I was just about to go back and do that. Thank you kindly for reminding me. Differentiation? I'm anti that. We are learning to anti-differentiate and evaluate indefinite integrals. We'll be successful when we can do some simple indefinite integration. So here's the setup for the problem that we're going to look at today. So Aaron is rushing to get his practice done and copy down his answer from Slater to the last question he was working on about derivatives. Looking back, he's unsure what the original functions were. Luckily, he came to your team for some help figuring them out. Your task. For each derivative that I'm going to give you, I want you to come up with at least one function that could have that derivative provided. Prepare to share your derivatives with the class. Now, that's what we do if we were in person. We are going to do something kind of similar. And by kind of similar, I mean it's not really similar, but we're going to use the kind of setup. But by the way, Aaron that I'm making fun of here, he also made this meme for me. So I'm like, I feel like that's fair. Normally, I wouldn't give it a second thought about making fun of a kid not getting homework done. But it's COVID and like there's a lot more important things than just getting like schoolwork done. So I want to make sure that I'm not overemphasizing the getting of the homework done. So anyway, that's why I'm curating this. Otherwise, I would just kind of let it go and be like, get work done. But I think it's important to point that out in this time. All right. Anyways, that's what we're going to do. Now to do that, go to student.desmos.com. We've only done one other activity in student.desmos.com this year. We're going to do one today. It's going to be a quick little activity. At most 10 minutes we're going to spend in here. So go to student.desmos.com, log in with your Google account, and it should put you right into Desmos Classroom. All right. So go to student.desmos.com, log in with your Google account, and it should put you right into this Desmos class. All right. Ooh, what's this message? All right, let's see. Thank you, Greta. Thank you, Elise. Thank you, Tyler. Thank you, Evelyn. So here's what you're going to do when you get there. And I'm going to, since I'm recording, I'm going to share screen. New share. All right. So you're going to match the derivatives to possible functions. The derivatives all are like c prime of x equals 0. All right. Anything that has like function notation in it is a derivative. You've got to match the derivatives to possible functions. There's one I'm going to do for you right away because I did it incorrectly. I set it up incorrectly. F prime of x equals 2. X squared and x squared minus 1 go with that. I'm showing you that one because that's wrong. It should be either f prime of x should be 2x, which is probably the fix I'm going to make later. Or these should be 2x minus 1 and 2x. So I'm just letting you know that's a match for you immediately. Oh my gosh. And look, when you match them, it tells you how many cards you have matched correctly. So I'm going to give you about 10 minutes to finish this. If you get done early, you can go to Schoology, go look at the presentation, and start like previewing what I'm going to talk about next. Okay. Cool. So I'm going to pause my share so that you can still see that. And I'm going to watch what you're all doing and celebrate when people get their first and second trios. Woo, Greta got a first trio. So did Elise and Evelyn and Lizzie. Woo, keep working on those trios. Oop, Emma just got her first trio. What up? And you should all have at least one trio because I showed you one. Do, 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 do. I'm going to pause recording for now because I don't resume recording. Do, do. All right. Resuming share. Hey, here's someone's that they got all the way through it. What up? It just happened to be Girolamo Cardano, who, if you don't know, is the father of probability. He's a drunken gambler. And he's like, I want to stop losing money. How can I do this? So he basically figured out probability so that he could lose less money. Fun fact. It's very interesting. That's part of the history of mathematics. It's just like a bunch of drunken fools who are trying to not be as foolish and get better about losing their money. But anyways, the thing I want to point out here, look at that. There's at least 2 to each of these. And the number at the end, the constant, doesn't matter if it's there or not. Like, look over here. Oh, geez. The only one I didn't. Oh, for like q prime of x. It could be e to the x or e to the x plus 1. It doesn't matter. The derivative of both of those is e to the x. Because the derivative of a constant is just 0. Which we also saw with c prime of x. Yeah, I wanted, so it came up. I would like to do more of these. I was just talking that I've been spending a lot of my time kind of just rehashing a lot of things I normally do in class. And I'd like to do more of these. I just had a flash of inspiration to do this one. So I'm going to try to do some more of these. Boom. So I'll keep working on that, especially as we get through chapter 4. And there's some slightly more difficult things that we're going to hit up. I would like to do that. So thank you for that feedback. I do appreciate that. Part of the reason we haven't done more of them is because kind of my shame spiral about like me thinking about, am I doing enough? Am I not doing enough? And to trying to be okay with what I'm doing. But I know I'm at a point with pre-calc right now that I think I can handle putting a little more and doing extra stuff for you folks to get some better experiences. So, yeah, I hope that helps you understand where we're at and why we're at where we're at. Here are some of the ones I came up with, by the way, for those same problems. There were a couple I cut out because it was just going to be a little bit easier. By the way, you just found antiderivatives. Wow. Wow. I hope you hear that, Jeff. Just you can hear Owen Wilson saying that. I really hope you can. So you went from f prime of x to f of x. Here's how we represent that with symbols. Now, I don't need you to fully follow what's going on with the symbols right now. What I need you to do is just kind of listen and pay attention and just try to do your best. This part, again, isn't required for what we're doing today, but it's just going to kind of inform what's going on next. All righty? Nice. I didn't know actually what movie it was from. It's Owen Wilson. I'm like, oh, Owen Wilson, oh my gosh. So we went from a derivative and we tried to figure out what was the original function. And we did antiderivative to get there. We tried to undo the derivative. It's literally the reverse process. Okay? We're trying to reverse the process of doing a derivative. If you look at the bottom, that's normally the thing we start with, and the top is normally the thing we end with. But we're flipping the process on its head. We're trying to do it in reverse and see what that is. So here's like the whole thing, and I'm going to explain what each part of this means. So here's how we represent all that with symbols. We use this integral sign to show that we are finding or taking an antiderivative. We call this general process when we use the integral symbol indefinite integration, because you get a function out of it. All right. Boomtown. All right. So let's explain what the heck is going on here, what each of these symbols mean. This first one is an integral symbol. All righty. The second thing, the f of x, that's the integrand. That's the thing we're finding the antiderivative of. We're saying f of x is the derivative of something. I just don't know what. And that's the question we're trying to puzzle out. The dx, it's a differential. That differential, it's the variable we're trying to find the antiderivative with respect to. So you can take a derivative with respect to x, or you can do an antiderivative with respect to x. So all of these things, we can do all this stuff. And I'm just trying to point out what that looks like. All right. Capital F of x is the antiderivative of f of x. So that is probably, again, there's a lot of new notation today. And that capital F of x, we're assuming that is the antiderivative of f of x. Okay? So generally, when we have a capital letter for a function, it's generally an antiderivative of some of the lowercase function. Not always, but most of the time it is. You should generally assume it is. Look at the context of the problem, but a lot of the time that's how it's going to be set up. This C is the constant of integration. What the constant integration is, as you noticed when you were pairing things up, it didn't matter what the constant was as long as the rest of the function was what it was supposed to be. Because when you take the derivative of a constant, it goes away. And the derivative of a constant is 0. So it doesn't need to be there. But you need to put a C on there when you're finding an antiderivative, when you're going backwards. Unless you have information to figure out what C is actually equal to. And sometimes you can do that. It'll just be like, here's the antiderivative, or here's f prime of x. What's f of x given that f of 2 is 7? And then you can plug in 2 and 7 and figure out what C is. Oh my gosh, once you do the antiderivative. Not too bad. So why dx? Could we do a dy? Sure. The differential, again, the d something, it's just a variable we're undoing the derivative with respect to. Again, antiderivatives are undoing derivatives. Everything else is treated like a constant when it comes to anti-differentiation. Here's what I mean by that. So an example of like this notation and the correct answer, the indefinite integral of 3x squared dx is equal to x cubed plus c. That's a complete problem right there. That's the setup and the answer. How would you figure that out? Kind of have to work it backwards. You have to kind of troubleshoot, puzzle it out. Like, honestly, look at it as a puzzle and try to think about what was the original thing. Another way to look at it is you're kind of doing Jeopardy. You're given the answer and trying to figure out what the question was. All right, there's that. So you could also do this with respect to a different variable, like dy. If you're going to do that with respect to a different variable, you just treat everything there like it's a constant, and you're doing the antiderivative from there. It feels weird, but it's okay. It's going to be okay. It's just, you're not going to do a whole lot of this on your own, by the way. This doing like the antiderivative 3x squared with respect to y. You're not going to be doing that. If you're doing that, you did something wrong. So you should always be matching up variables with the correct variables and such. Like you should be doing this top one, not this bottom one. If you're doing this bottom one, something went wrong. Earlier in the year, I shared this with you. The derivative of position is velocity. The derivative of velocity is acceleration. You can go the other way too. So the antiderivative, or the integral, indefinite integral of acceleration is velocity. The indefinite integral of velocity is position. Now, technically, it's a little bit more. The indefinite integral of acceleration with respect to time is velocity plus initial velocity, because initial velocity should be a constant, which is why that makes sense. The antiderivative of velocity with respect to time is position plus initial position. Hey, that's it. Just kidding. There is a little bit more in the section, but basically it's a couple more examples that we didn't do. And it walks through how to do like a position, velocity, acceleration problem. So I'm going to leave you to do that. And there's also, I have an example in the post credits. I forgot about that. So you can go check that out on your leisure. Oh, last thing. I'm going to stop recording because I don't need to record this part.